Hello, everyone, and welcome back to another inGenius Prep Series session. I hope I'm audible and I can see some comments coming up in my screen. So, this series of webinars, as you have been attending from the start of September, is coming to an end with these true interesting webinars towards the end. So, in this penultimate webinar, what we'll be seeing is we'll be talking about a field which is currently causing huge strides in technology. Before I start, a little intro about myself. I am Joe, studying in PS University, currently in my third year. I work as a backend developer in a startup, and I'm also one of the core team members in DSC PESIT since the last 2 years. I am an AI enthusiast. I love solving problems and building products which involve ML and AI. Along with me today, we also have Joy, who is a friend of mine and also a core team member at DSC. He is very passionate and also experienced in this domain. He's still in his second year at PES and he has already done some amazing projects and has written tech articles too in Medium. So let's get started with the session. As you can see on your screen, there is also a link which says ask a question at slides.app.google. So if you are hesitant to ask on the live stream, you can also go to that link which is present and that should be there in the description too. So click on it and go ahead and you can ask questions and you can be anonymous too while asking questions. So there it is. So I'm sure many of you are fascinated to know what powers intelligent systems such as those in a Tesla car or applications like facial recognition system like the AI filters in your phone camera and Snapchat filters and even like the streaming platform that I'm using. I can use backgrounds and irrespective of whether I move, my face will be clearly seen. And you guys would have also used chatbots. So those which converse with you like a real human being talking to you from the other end. You might have also heard about GANs. So these are bringing huge applications in the field of fashion and even science. In the field of fashion, if you see, GANs can be used to in-paint photographs. So like here you see a Mona Lisa photograph shown in different ways. And how does this help? Well, you don't have to recruit a model or a photographer or even a makeup artist or pay for a studio and a transportation. GANs are also used by scientists to improve astronomical images and so on. So all these applications that you see, what is common in all of them? The thing that is common is that they process huge amounts of data and these solve these complex problems. So you might be thinking at the back of your mind, so is it that only big companies like Tesla and NASA and OpenAI can do all this? And maybe I can't do any of these stuff? Maybe I should only understand the concepts since I won't be able to see the results visually. As a human, that's a tendency. We always kind of expect an output out of anything that we do. But today, through this session, you'll get to know that if you had told me this question that I can't do much 5 years back, yeah, you're right. But today, there is a huge boom in computational power, and there are better techniques which have led people to take an interest in neural nets. And even there's a huge stride in this technology. So, deep learning does require a lot of years of study, but today we will see like with frameworks like Keras, anyone without a background in machine learning. So you may be a web developer, you may be an app developer, but you can quickly enter this field by just knowing some simple programming concepts. So we will see some examples in this webinar. You will be able to apply these concepts to your own problem and leverage deep learning in your hackathon project. Before I get started with the agenda, I would like to mention about inGenius. inGenius 2020 is our annual hackathon organized by PESU ECC Computer Science Department. It's the annual 24-hour hackathon, and this year we are entering the ninth edition. Surely, inGenius has come a long way since its inception as one of the first hackathons that have been held in Bangalore. We also have our live partner social media site called Amigos. They have helped us in giving cash prizes for those who participate in our quiz. Talking about Amigos, it's a social networking site for college students. You can connect and share with your friends and your fellow college mates. You can browse and apply for internships, prepare for jobs and higher studies, and even find suitable scholarships for you. We are really glad to have them as our sponsors for this webinar series. And throughout all the entire series, we have been getting a huge amount of viewership from not only our college, but even all over the country, many college people. So if you are someone who is not a part of PS and you are looking at this webinar, do sign up for our inGenius hackathon. The dates for the registration we will let you know, and we can't wait to see your amazing ideas come into product. So without any further ado, let me go through the agenda for the session today. So if you're a beginner and you do not know much about deep learning, you should pay attention to the first half of the webinar because we are going to talk about the basic overview of what a neural net is, how is it going to help, and all those stuff. And if you are someone who knows what a neural net is but hasn't implemented one and you want to get to know about that, you should probably continue staying with us for the last half of the session where we will show you three demos of using neural nets in your project. So now I would give the control to Joy, who will be going through the basic overview of neural nets. Yeah,
Thanks,
Joy,
Joe, for that
I will
amazing
add you to the
introduction.
screen. Yeah, you are live now.
Yeah, cool. Thanks, Joe, for that amazing introduction. Okay, let's start up today. We're going to be learning about basics of neural networks and deep learning. Before we start, I'm pretty sure most of you have come across these words like data science, artificial intelligence, pattern recognition, machine learning, deep learning, NLP or natural language processing, image processing, computer vision, speech technology, and reinforcement learning. We will be playing around with few of these words, not all, and maybe at the end of the seminar you'll have a clear aspect of what exactly those are. First up, we have AI. What is AI? Artificial intelligence. Artificial intelligence means getting a computer to mimic a human behavior in some way. If we take, for example, every human has his own set of abilities, like, for example, vision, hearing, or maybe understanding a text told by someone, or writing a text in a format that someone else will understand. This, which when we mimic in a computer or with a program, it's called computer vision and natural language processing correspondingly. These are mainly mimicked or implemented using a computer program using two main approaches. I would say there are many other approaches, but then just stick to the two approaches. Those are machine learning and deep learning. This chart here is quite important. Deep learning comes under machine learning. It's a subset of machine learning, and machine learning comes under the huge umbrella of artificial intelligence. So basically, AI, ML, and DL all are interconnected fields. Where ML, machine learning, and DL aids AI providing algorithms and neural networks to solve data-driven problems. Coming to what is machine learning and deep learning, I would say machine learning is a way of developing programs, computer programs, which when fed with data, learns from it automatically without any human aid. So basically, if you want to perform a task T so you train a machine with experience E. What happens is it learns from that task, from that experience E. It has a, I mean, it learns from the experience C to perform task T, and then once the training is done, we could try it with new data sets which the machine has not seen while training, and hope that it predicts something useful. It will predict something useful if you have trained it in a better manner. So coming to deep learning is a subset of machine learning that deals with neural networks and other complex techniques to help AI learn. Deep learning mainly comes to play when the data set is too complex or the problem you're solving is too complex. The meaning of complex here is when our data points are not linearly separable. What exactly that means, we'll cover it in like after 2 or 3 slides. So just as the name suggests, deep learning here, a deep learning model aims to always replicate a human brain or mimic a human brain basically. Why neural networks? So here are we going to learn about that linearly separable. Consider that X and O are the data points for us distributed here. X represent the female category, and maybe circle represents the male category. So given any input, we'll need to predict whether that input belongs to a male category or a female category. If we linearly separate it, the accuracy is going to be really bad. You can see in this data points how they're distributed. There are few male data points in the female section and few female data points in the male section. So any linear algorithm, any linear classification algorithm wouldn't do a very good job in classifying this. So boom, we have neural network that comes to our help, which draws a non-linear decision boundary, which helps us classify in a much higher accuracy and in a much better way. So that's the main use of neural networks, and when exactly a neural network would be used. You can see in the graph C where it draws an exact decision boundary around the data points we need, but that's like more sophisticated techniques to build models. Let's not go too much into that. Let's start off with neural networks. What's a neural network? Neural networks form the base of any deep learning model. Basically, deep learning uses artificial neural network which mimic the human brain to solve complex data-driven problems. Coming to the main point, the basic unit of a neural network is a neuron, artificial neuron. In our brain, it's a neuron. It's almost loosely connected, the ideas of them working. Again, talking about a neuron has a set of multiple inputs and only a single output. Right here is an example of a neuron. Here we feed in multiple inputs from X to Xi. Then I'll come to what's weights and bias in a while. And then some computation takes place inside a neuron, and then it comes up with only one output. Again, each neuron is associated with a particular weight with a different value attached to it, and a particular bias with a different value associated to it. These weights and biases are trainable parameters, which are randomly initialized at the beginning. And once the model is done training, they have a specific value which can be used in future for better predictions. I'll exactly tell you how exactly the values of weights are altered during training in a while. Now, when I say neuron, I just want you to imagine it as an entity that holds a value, which the value on which computations are performed to produce meaningful results. So the computation that's performed in a neuron is nothing but the input given to it multiplied with the weights, and there'll be n number of inputs, right? So each neuron is connected to all other neurons in the next layer. So when we compute the sum of products of the weights and the inputs, we get a specific linear value that is then passed on further layers for further computations. There is a slight mention about activation functions here. I'll come about that also in a bit. Let's illustrate the working of an entire neural network with just one example here. Here we have three neurons and one output neuron. These two are the inputs we are taking in. So the task we are trying to perform here, given an animal sound, we need to classify whether it is a dog's bark or a cat's meow. Dog's bark is represented with 1, 0. Here the 1, 0 is nothing but x1, x2 vectors, and cat's meow is represented with 0, 1. Again, like I mentioned, the weights associated to each neurons are learnable parameters, so we just randomly initialize them. Now we set something called as threshold. Like if the product of our inputs and the weights sum together, if the value is more than 0, then we classify it as a dog. Again, if the product of the weights and the inputs are summed, and if the value comes to be below 0 or any other negative value, we classify it as a cat. So with the random value of our input weight and the given input x1 plus the random value of the again weight w2 with our given input x2, which is in this case, in the first case 1, 0, we feed it in. Again, in the output layer, we expect during the training progress, we expect that this computed value should be greater than 0. So as at the end of training, our model will be able to learn the values of the weights, which precisely comes out to be with W1 as 1 and W2 as -1. Again, -1 doesn't represent that the sign has nothing to do with the value that it holds. Doesn't mean that the value we predict is wrong or something. It's just a value, because if W2 is W2 is the weight associated with the cat. So if we need to get a negative value when the sum is computed, we need the weights to be negative here. Again, we are ruling out, you might ask, there's a probability of why not feeding the inputs being 0, 0 or 1, 1, which is not possible because 0, 0 indicates that there is no sound being inputted. So we can't really classify what in the output. Then 1, 1 means both the sounds are being inputted. And again, that doesn't make any sense, right? So we need to classify whether the input sound is a cat's or a dog's. Coming to the activation function. Now, when I talk about neuron, I want you to imagine this. Every neuron is divided into two partitions. The first one is where the computation takes place, that W1 into X1 plus W2 into X2 and so on. That results in a linear value, which is literally of no use to the neural network nor for us. So we need to scale it down to a non-linear value where we can perform operations on it. There are n number of activation functions. Generally, the most used ones are sigmoid, ReLU, tanh, and leaky ReLU. We'll be just discussing about sigmoid in this slide. The given formula here is the formula for our sigmoid function. The value that's computed in the first partition is passed as z here, which then results in a non-linear value between 0 to 1, which is passed on to the further layers for further computations. Now, again, the main use of activation function is when it decides when a neuron should be fired up, and not all the values that are computed in neurons are passed as output. That's one thing we need to remember. So if the value computed at the activation partition is more than a minimum threshold, then the neuron is fired up and the value is passed to the next layer for further computations. You can read about the definition here. Activation functions are generally applied to the computed neuron's value from the first partition, that is, to map it to the expected outputs. What's a feed-forward neural network? A feed-forward neural network, or just a neural network, has many number of neurons that constitute it. Now here, again, I'll explain each layer in detail. The first layer being an input layer, with the name, as the name suggests, I guess, obviously the input is being passed here. Each neuron has weight associated to it with the different values, which is initialized randomly. And then now we come to the hidden layer part. There could be n number of layers here, but still they all together constitute as one hidden layer. More the hidden layers, better is the learning rate and better is the accuracy we get at the output. And then the final neuron represents our output function. So this is just a feed-forward neural network. Here, no calculations or no change of weights take place. We are just inputting, calculations take place, and then we're just predicting what would be the output. One important point to be noted is the weights of all the connections are solely different. If they are same, every neuron is going to end up computing the same value. So we generally initialize it with different random values for a better accuracy. You could read about these points here. I would give about like 5 seconds for each point. Coming to the backprop network, this is the main part of any neural network. I would even define this as the brain of a neural network. This is where actual learning takes place. Picture. We would be given a set of input data and the output we expect. While training, we do have the output that we're expecting. We can't change. Now there'll be like a randomly initialized weights value for every connection. Now we can never play around the input values; they're always constant. So we compute the neuron's value here, pass it through the activation function. Again, there's another value computed here, and then there's a final value computed here, which is nothing but the input from this neuron, the input from this neuron, multiplied with their respective sums and added up, passed through an activation function. Now, the value we predicted in the first epoch or the iteration is compared with the actual value that we're expecting. There would be obviously difference. For example, we're expecting value 1 to be at the output, but then our neural network is predicting something like 0.4, which is obviously bad, which is not even close to our value. So then we compute a difference now. This is called the loss. So we compute the difference between the actual value and the predicted value, then sum them up for all the inputs. This sum of the whole losses is constitutes a term called the cost function, which when you're doing in the program, you'll get a better intuition of what exactly it is. So this cost function is a little important value because this is what's going to determine how well our what's going to help our neural networks rather to learn. So once when we calculate the cost function, we find the negative gradient with respect to it. We pass it back to our hidden layers, and we tell where we now update the weights were initially randomly initialized. So now we would know that the what's the difference between our with our actual prediction and the expected output is because of the weights, because inputs value cannot be changed. Now we alter the value of weights according to the negative gradient. Now for the next iteration, again the new altered weights is multiplied with the inputs. Computation takes place here. Again, it's passed on to the next layer. Again, there's a value here, which is fed as input to the output layer again. Now our value would be like pretty close to the predicted value, somewhat like zero point 0.7 or like 0.77, which is again not good. So what we do is any neural network model goes about like 20 iterations of forward and backward propagation to get a perfect neural network that can predict anything useful in future. Maybe after like 20 iterations, our output will be 0.999, which is a really good value because the difference in loss is like pretty less, and it's almost predicting the exact same thing. Now, what we do is after training, we save those weights. We save those weights, and then we test it on a different sets of input. That's different set of input as in that the model hasn't seen before, to see whether our model is predicting an exact or like the expected results. Usually, suppose I would demonstrate with a better example in the next slide. Yeah. Here we can see there's a this is an this is a neural network that's predicting digits between 0 to 9 with the input image given. The input images of dimensions 29 to 29. So there will be 784 pixels, 29 into 29, or simple math. Then coming to the part, this is an already pre-trained neural network. So basically the weights values are correct values for predicting any digits. Now, after we pass in the pixels to the input layer, the hidden layers, each neuron is associated to a specific pattern. For example, when we see this 2, we recognize it as 2 by seeing that this curve and this curve attached together. Like, it's not some magic that we see a number and we directly recognize. We recognize it by looking at the patterns of what it's made up of. So suppose 2 is made up of 3 patterns. We could say the first curve here, the second curve here, and the third curve here. So basically, the first neural network, the first hidden layer would have such kinds of patterns because 9 would have a different pattern, 5 would have a different pattern. So there'll be generalized patterns in the hidden layers. Now, once when you pass in the inputs, based on the each pixel value, every neuron is light. The specific neurons related to the digit is lit up, and then once put together, it resembles pretty much a digit. So in the last output layer, these neurons will be associated with specific probabilities. For example, here probability of 0 would be zero point 0.1 of whether the input image was 0 would be zero point 0.1, and 1 would be like maybe again zero point 0.1. Then 2 will be like 0.99 or zero point 0.8. Then 3, since it looks a little bit similar to 2, will be like around 0.9. So now we explicitly set up a threshold. If the probability or the predicted value of each of a neuron is above this threshold, then that is the number. Here we'll set the threshold as maybe 0.6. So since the neuron representing the digit 2 has a threshold greater than 0.6, it classifies the input images digit 2. That's it from my side. Joe will be taking up a normal coding session for deep neural networks.
Yeah,
Joe, are you
thanks,
audible?
Joy. Yeah, thanks for running through the basics. So now I will begin to share my screen. Yeah, so we went through the basic overview of, what a neural net is and stuff. And some of you might ask, as in last 2 days back, you might have seen a linear regression model, a logistic regression model in the previous webinars. And you might say that even they have the ability to take in data and produce results and stuff. But the real power behind neural nets is that with classification or basic regression models, the input can't be anything. So your input might just have to be of one type. So like maybe like a one-dimensional vector or something. But with neural nets, that's not the case. I can accept an image and that can in turn produce another image. And that gets quite impressive because the applications are huge when you come to talking about neural nets and stuff. So now let's put a stop to the learning component and we'll get into the coding. So those of you who just heard about deep learning, this first code is kind of for you because in a matter of minutes, you'll be seeing a simple neural net running in front of you. So what we'll be using for that is the Keras library. So what is Keras? Keras is a deep learning API which was written in Python and it runs on top of TensorFlow. So assume Keras to be some kind of a layer which is running on a low level TensorFlow compute engine. And yeah, so that's about Keras. And basically, you can use it to solve machine learning problems which focus mostly on deep learning. Why Keras? This answer is there on the documentation itself. So you're able to go from an idea to a result as soon as possible. So that is a key when you're doing any research with deep neural net because you can't keep doing the math part of it and maybe say I got a result. That doesn't work. You would obviously want to see some kind of output. And these kind of frameworks such as Keras and PyTorch and TensorFlow, these help you in this. So let's quickly get into the coding session. Today I'll be using Google Colab, and if you haven't heard of it, Google Colab is like cloud-based system which Google provides you, and you basically don't have to install anything there. So you will freely get to use Python and Keras and all your other data libraries such as NumPy and Pandas and all those. So you are kind of ready to go. And another use of Google Colab is that it gives you a free GPU. And trust me, a GPU can save a lot of hours and hours into training time because some of these neural nets train real quickly, especially when you consider one dimension data, when you're feeding a one dimension data as an input, then yeah, it does train it fast. But when you're considering about images and videos, or maybe if you're going to generate some text or something, then that takes a lot of time. And at this time, GPU is the way to go. So I would suggest you guys to hop on to Google Colab now. And you can also find the link in the description to my GitHub repo. And this is the resources that we compiled for this webinar. So now we'll be going through this, which you can see here, the dnn.ipynb. So once you open that, you should be able to see this on your screen. Yeah. And you will see a button here which says open in Colab. So you will be able to open this code directly on Colab if you have linked your GitHub and Colab together. If you haven't, don't worry, you can have a look at this and maybe copy paste it into Colab or whatever works. So since I have opened it, you can see that this will how it look when you start on Colab. So if you are Google searching Google Colab, then you might see this page. So here, these are all the previous Colab notebooks that I have opened. You can see some examples where they show guides and how to use Markdown and all these forms, how to access files and all those. So you can go through them. You can also have these notebooks stored in your Google Drive. So all these are stored in my Google Drive. So that's why I'm able to see here. If you link your GitHub too, you can open them directly. But yeah, it'll ask for a simple authentication. That shouldn't be a problem. And you can also upload a file. So basically an IPYNB file. If you're someone who use Jupyter Notebook, so you can upload that directly here, and you'll be able to see your code running here. So and this is how it'll look initially if you're coming through Google, if you're searching it and then entering this. So since I've opened it already in through my GitHub, yeah, we can get started with the code. So let's see what are the steps that will be involved when you're going to build your first neural net. So these are like the basic steps that you have to do. You have to first obviously load data, and then you define something called as a Keras model. So Keras has few things which I will come back later to discuss. And then we obviously compile the Keras model, fit the Keras model, evaluate Keras model. All this might sound weird, but after the next 5 minutes, you should be able to get. So let's import the following libraries. So we will be using mostly Keras and Pandas. So Keras is, as I told, for building the model, and Pandas is just to open the CSV, whatever is present in it. So about the CSV, if you guys want to run with me, you can go back to my repo and clone this repo in your local system. You'll be able to see this pima.csv dataset. So what this is this data set is basically something that tells how how easily someone can get diabetes or something like that based on some input. So I can just show you that. Yeah, so here if you see this, these are the different columns in that data set. So this is like the number of times that person has got pregnant, and this is like the plasma concentration, blood pressure, skin thickness, serum concentration, BMI, and diabetic concentration of the blood. That's some science technology. And this is the age. And this variable in the end is basically to tell whether that this person who had all these attributes, whether he ended up having diabetes or not. So one is for that person had diabetes, and zero is that person didn't have diabetes. So once you go back to the Colab, if you want to import the data set, all you have to do is go here. You will be able to see this structure, and you can go into content and you can just upload the data set if you have it stored in local. So right now I'm uploading the data set from my local repository. It just tells me that uploaded files will get deleted because the runtime is recycled. So that's not an issue. And yeah, as you see, the CSV is uploaded into my Colab directory. So to run the cells in Colab, many of you might know, you can just stay on the cell and then click on Shift Enter. And yeah, okay, yeah, I'll just run that. Cool. So the first step is done where we import the libraries. Next up, we'll have to load the data set into our thing. So if you guys know Panda, this should be easy. You're just reading the CSV, and then we will check how the CSV looks. And if you have uploaded it properly, like how I did, you should be able to see this. So the head has head will show like the first five of the data set, so you can see all that. And yeah, if you want to see how many columns are there, it's 9 columns and 768 rows. So now I want only, so I'm basically going to split this into two. One is the X component and the Y component. So for the X, since I have all these variables, I'm just going to drop this variable column because I'm going to take that as my Y variable. So that should be the output of the neural net. So I'm just going to say X is equal to df dot drop columns equal to variable, and Y is equal to this variable. So that should work. Yes. So X will have all the columns other than the last variable column. So these are basically the input for your neural net. And Y will have the one variable column, which is basically the output that you expect your model to give. So our next step is we are going to define a Keras model. Now this is important. All these what I discussed earlier, you might already know because most of you should be familiar with pandas. So what we are doing here you can see I'm saying model is equal to keras.models.sequential. So what is this? In the previous thing, what Joy explained, you would have seen that neural nets were some kind of layers. So let me go back to my presentation. And there are two kind of models which you can do. Before that, I'm just going to tell you the three fundamental things which you will need in Keras. First is a Keras tensor. So Keras tensor is something, the way in which you can represent data. So we represent data in the form of tensors. And this Keras tensor will come into play when you're usually using Keras through TensorFlow. Otherwise, if like for instance, we are just here directly importing Keras, we aren't using it through TensorFlow. So in this case, we have only two important stuff to keep in mind. One is what is a layer and what is a model. So what is a layer? A layer is like a kind of object which basically does transformation on whatever input you pass it. So layers is like a group of neurons, as you saw in the previous presentation. And what is a model is a bunch of these layers, and the model will be given some specification about what kind of loss function do I want to give, what kind of optimizers I want to give, and some other attributes as such. So these are the two ways in which you can build models using Keras. So quickly, let me just show you the difference between sequential model and a functional model. So sequential model is just like a layer by layer model. So this one disadvantage of sequential model is it doesn't allow the models. You can't basically feed multiple data into these kind of models. But with the functional model, it's very flexible because the layers connect to more than just the layers don't connect to only the previous and the next layer, so they connect to more than that. And these will help us in creating complex networks. So we won't be using functional neural nets today, but I'm just giving a quick overview about that. So let me get back to my presentation. So here, as you see, now you might understand what is sequential here. So I'm basically telling my model to be a sequential model, and I'm defining that as an object to model. Now I can add how many ever layers I want. Things that you have to keep in mind: the input shape. Input shape, make sure it's correct. So we saw that my X had 1, 2, 3, 4, 5, 6, 7, 8 columns. So I'm going to say the input shape is 8. And the number of layers that you want for the input layer, it's always better you keep it higher than the input layer, or you can keep it 8 itself. That should work. And you would have heard Joy talking about activation functions and stuff. So I am going to give an activation function called relu for this first layer. And similarly, I'm going to make another layer just because it might, help me make it better. And a question might pop up for you now. I mean, how do I know the number of layers and what should I do? And this is like a very hard question to answer because this is basically trial and error experimentation. And the if you want to get a good result, it actually doesn't depend on the number of layers. Well, it does. It should be more than the inputs so that it can give some output. But there are also things like you need to feed in a larger data set. That data set should have correlations and number of epochs and batches and all that matters. So yeah, so in this code, we are just going to see three layers, and these are fully connected because it's a dense. So I called it a dense neural net. So that means it's fully connected. And the activation relu, I am using it as that function. And for the last layer, that is the output layer, I'll be using sigmoid. So this model basically expects 8 variables from me, and the hidden layer is 12 nodes, and the next layer will have 8 nodes, and then the output layer will have a single node to give you the answer. So let me run this. So if you can see, the cell has run. So basically the model has been made. Now we will look at compiling our model. So we have already defined what our model is. Now we are going to compile the model. So what does compile mean? So while compiling, we need to say some additional features for the model. such as what is the loss function and some attributes like optimizers and stuff. So in this case, we are going to use cross entropy as a loss argument. And you may not know what cross entropy is. You can always Google and search it since we don't have much time. And why binary cross entropy? Because you saw the output had only two answers, that's 0 and 1. So let me just compile this. So compilation is important to see your models running. Next, we do something called as fitting the Keras model. So now that we have defined the model and we have compiled it, it's time to put in some data into the model. So that is the process of fitting. So we either train or fit our model on a loaded data by calling the fit function. So here you see two things. One is epochs and one is batch size. And obviously, the first two arguments are our input and our output. So what is epoch is? Epoch is one pass through the entire row of your training data set. So if I pass through all the rows of my training data set once, that's called one epoch. And what is batch is one or more samples can be considered by the model when the weights get updated. So, for instance, one epoch can comprise of one or more batches. So, given this batch size that is 10, my model will run for 150 epochs. So, if you want to know more about this, you can always Google. It's a very simple concept. You should be able to get that in a few seconds. So now I'm going to fit this model, and this does take some time because there is 150 epochs, but since this is one dimension network compared to the other networks, it should be very quick. So here we see that almost, yeah, we are done. So basically the Keras model is now trained with your data. Well, it's job done, but what is left is I want to see what my model is able to predict. So for that, we are going to evaluate our Keras model. And for this also, there is a function which says model.evaluate. Will basically return your loss and your accuracy. But now I can see here the loss. It shows an accuracy about 77% and the loss is around 47%. And this is on the training data set. So let me just check the accuracy, and we see that the accuracy is 77.73. Now, I am going to make some predictions with the data I have. So, on whatever data I have trained, I'm just going to see what kind of predictions my model is going to make. Obviously, we have trained it only for 150 epochs, and I'm assuming 77% of it should show us the right result. So, let me just run this cell. Yeah, so here if you see that when I provided this as my data, I got 1 as the result, and obviously the Y had 1. So it expected 1 and returned 1 to me. So yeah, my model has done pretty well. So that's good. All my 5 outputs are right. But that may not be the case with you if you have got a lesser accuracy. This because it might mine would have trained it on a better batch or something. So that's why I'm able to get all my answers right, but you may not get. Uh, yeah. So next we'll be looking at, this is important when it comes to hackathons and stuff. So I'm done with this model. What do I do with this? I can't leave it in Colab itself. I want to deploy it somewhere. And to deploy it, you have to obviously save it somewhere. So this method provided by Keras will help you to save the model. So I'm going to say model.save, and then there are different formats. You can use the H5 format. You can store it as a JSON, and you can store it as a YAML. And if you want everything to be in one file, like the weights that you have used, the inputs that you have used, everything, if you want in one file, I would suggest go with the H5 format because it basically compiles everything. So let me save that. And to just check if that was my model, yeah, here you see that I call the old model, which is basically I loaded that model into Keras again, just to check if it was the same model. So here I see that I've got 77.73, which is pretty good. Yeah, so if you had coded with me, you would have seen these results. You might have seen another accuracy. But yeah, this is your first neural net basically. So now we have seen how do we build a simple neural net in like very quick time. And this is only a tabular data, which the neural net, I fed it as an input, and it was able to give me good results. Next, we will see another application, another entire kind of neural net called as a convolution neural net. And now I will give the sharing back to Joy because he'll be showing you how to build this convolution neural network in a Kaggle notebook. And this is important because many of you might find Kaggle contests online. And if you want to code it in a Kaggle notebook, this is how you should go ahead. So I'm going to give the control back to Joy and he will show you how to build a simple convolution neural net. Over to you, Joy.
Oh, thank you, Joe. So now we'll be learning about what exactly are CNNs. Neural networks, what we saw in the previous example and my explanation was a dense neural network, which is the most simple form. Over the years of advancement, there has been different types of neural networks like convolutional neural network, recurrent neural network. Now, both we'll be describing both in this tutorial. RN will be taken up by Joe right after this tutorial. So, what is a convolutional neural network? A convolutional neural network is a neural network that has one or more convolutional layers. I'll tell you what exactly is a convolutional layer and are used mainly for image processing and classification. So since CNNs are used for image processing and classification, we are going to carry out a prediction of whether a given input image is a dog or a cat. Let's get started. I hope you guys can see my mouse pointer. Now consider this as our input image. Obviously, it's not making us any sense. Usually, consider this as maybe a dog's photo. For human eye, it looked like a dog, but then for a computer, it's just going to be each pixel values. Here there'll be pixel value, here there'll be pixel value, here there'll be pixel value, so on for the 5 by 5 matrix. Now, the pixel values are always between 0 to 255, and this would make some sort of sense to the computers. When we see a dog, how do we recognize it's a dog? Like, how does a brain recognize it's a dog? Maybe the ears, the mouth, the way it barks. There are so many other features. So for a computer also, we would be feeding, we would make sure computer recognize these features to recognize the given input image as dog. So what we do is we take the input image, we take a 3 by 3 filter. The you can see the highlighted, the dark shade is a 3 by 3 filter. We slide it over the input image one at stride length equal to 1, which means like first is this 3, next is this 3, and so on. So when we slide over that way, the important features in that region is noted down in the what do I say pixel here. So once after one convolutional layer, we get a image of sort this way. Let's come to the image on the right side. Here, this is our input image. You might ask why there are 3 channels. Usually, any image is colored images. So the color stands for RGB, but in Keras it's BGR, I think. So usually what we do is we scale it down to grayscale so that it's of only 2 dimensions, the height and the width of the image. That saves a lot of computational power and energy. Let's take up an example with RGB1 itself. So here the 5 by 5 represents the height and the width of the image and 3 represents the number of channels RGB. Now we have to slide over a filter over this input image to recognize the patterns and features, detect mainly its edges and stuff. Once when we slide over this filters over this connet right till here, we would get a matrix like this. This matrix, when we take a look at it while training the model, wouldn't make of any sense. But then this makes a bit of sense to the computers because it recognizes the most important pixel values that a computer would understand, recognize what exactly a dog is. Usually, n number of filters are applied. In our tutorial, also we'll be applying like 40, 50 filters and stuff. Here, in this example, we're applying 2 filters, the first one being this, and the second one being this. This, for example, might detect all the vertical edges. This will detect all the horizontal edges. And then we stack up these layers to give it as an input to the model. One more thing is, this is again a 3-dimensional vector. Before we pass it to our final layers, we have to flatten it. When we flatten it, there's no loss of data. The data is transformed to a 2D arrays. Next is max polling layer. Again, I told you each pixel will have its pixel value between 0 to 55. That would make sense for the computer. But again, not all the pixels in an image would make sense, right? So what we do is we again take a window size, maybe in this case it's 2 by 2, and then we max pull it. Max pull as in this 2 by 2 window, whichever value is the highest, we only store that. This way, we make a note of all the important features without any loss of data, and we even remove all the unuseful features for the pattern to learn, for the model to learn. The main reason why we do is this reduces the size of the image. So when we pass it to the model, the training time is reduced considerably. Let me just give you an overview of how to set up a Kaggle notebook. The reason I'm using Kaggle is because my data set is from Kaggle. We could just directly import it rather than downloading it and loading it on your Jupyter notebooks or anything else. Come to the notebooks bar, new notebook. I already have a notebook ready, so I'll just be running the cells. I'll teach you how to set up a notebook. Python. There are n number of languages. Just give Python. This will take some time to set up. Yeah, it's done. Now, a few basic packages like NumPy and Pandas are imported. This is quite important because this Kaggle input specifies this tab right here. Here's exactly where you're gonna input your data set. We would be using something like dogs versus cat data sets that has images of both. So let's search for it. Is this the one? Yeah, this is the one, 816 MB. You need to add it here. Now, the moment this is a zip file, so this is one of the way to iterate through any zip files. Now this will show what exactly are there in this directory when I run the cell. This will take a bit. You can see this has pictures of dogs and cats. Before I start off sharing my notebook with you, I'll just show you how exactly this data set looks. These are just the file names. When we access the file name, we'll get the actual picture. Let's go to my notebook first. Yeah, cool. Okay, before running it, let me show you how the data looks. Yeah, you can see, right? The name of the file, the name of the picture would be if it's a cat separated by full stop and the number. The separated by full stop is a quite important thing because we'll be segregating or loading all these images to a list based on that only. So remember this, the files, the picture's name will be what animal it is, full stop, and the number. So these are few cat pictures. Let me show you some dog picture. Yeah, we would need this many data. If you ask why there's so much data, in fact, we would need more amount of data to have a better model prediction. Yeah, there's dogs here. Yeah. Now let's start off with the training. First, again, we run this cell to see what exactly is there in that zip file or the directory we have inputted. This will take a bit to run, maybe like 5 to 10 seconds at most. Yeah, we can see there's a training data set and there's a test data set. Test data set is the one that you test your model with, whether your model has learned properly or not. Ignore the sample submission.csv because this data set was part of a Microsoft challenge, so this was something to do with that. Now, so you can see that what's exactly under this data set. We need to import zip file because we'll need to unzip the train data. This is exactly the syntax for unzipping. Zip file. So we're just going to write. So now inside the zip file, there will be 3 different files again. /train, and now we close this zip file, zip reference instance. What exactly os.list directory does is it creates a list with the file names inside the directory, inside the training dataset we have mentioned. So the file name inside the training dataset was dog.1, dog.0, dog.2, cat.0, cat.3, that way. We declare an empty list for categories. I'll tell you what is it. So now we are iterating through the file names. The file names, again, I told, is dog. Like for example, take the first file name as dog.0. Up, and when we access the 0th element, it's nothing but dog. So if the category is dog, we append 1. And if the category is cat, is covered in this else condition itself, we append 0. So I'll tell you what's the main reason why we're doing it. We're creating a data set as of now with only 3 columns. One is the serial number, another is a file name, and then what category it belongs to. If it belongs to dog, we classify the category as 1. If it belongs to the cat, we classify the category as 0. Okay, we are done creating the dataset. df.head will return the first 5 elements of the dataset. We can check it out here. Yeah, cool. You could see that dog dot the 890th image of dog is classified to be under 1, and then the 3660 image of the cat is classified to be 0. These are few important packages that we're going to be importing. Keras.sequential, Keras.models.import sequential. You learned why we are using sequential, because there's only one difference between sequential and functional is sequential can handle only one input, whereas functional can handle multi inputs. Then dense layer. This is the dense layer of what tutorial we saw on the previous one, which Joe explained. And then convolutional 2D, I explained what it does. Then max pooling also. Then flatten also explained. Activation functions also explained. These are just other basic packages we'll need. Load model is to save our weights of the model. Then Keras.backend I'll explain you a little bit later why we have imported it. Even image data generator. Then Adam optimizer is just a gradient descent with a lot of modifications to give a really good accuracy and fasten the training rate. Now from sklearn, we also import train test split. Basically, any data set, we usually split it with 90% for training the model, 90% of the data for training the model, and the remaining 10% for testing it. We're also importing another package called image to array, where we'll be converting an image to an array. Again, image as in is the pixel values which the computer will be seeing, and that is converted to an array. Then from keras.utils, we import 2 categorical, which one hot encodes the y labels. Again, I'll come back to that part. And then matplotlib.pyplot as PLT for showing you how the loss function would look. Let's run this cell. Cool. Now we'll need the most important parts of developing any DL model is first you have to define your model architecture, and then your training variables X, and then your what you're against training, your expected outputs Y. So the data is an empty list, labels is an empty list. Data would usually contain the pictures of dogs and cats, and the labels would classify it whether the picture at index 0 is a dog or a cat. Suppose at index 0 of the list there's a dog, the label at index 0 will also have a dog, but then one hot encoded, as in if it's a dog, it's representing 1. If it's a cat in the next class, it represents again 1. Now this is the path to our training data set. We iterate, remember we created a data set in the beginning with file name and the classes and total number of elements. So we iterate through it. The image path would not be nothing but this dataset's path plus the image name. So that's exactly why we are adding it here. cv2.imready would return in the image, and the reason we pass 0 is we converted from RGB to grayscale. because color in training model that classify whether it's a dog or cat actually doesn't matter, because it wouldn't matter anyway, because there are like n number of colored dogs and number of colored cats, so there's no point having color. Then we'll need to specify, because every image you have seen in the data set was of different dimensions, like one might be like 200 by 200, other will be 300 by 300, so that wouldn't make sense, right? Everything should be scaled down to order. We are scaling down to 128, 128. Then we further reshape it to a single column vector without any loss in data, because we are having all the 128 into 128 pixels. Now we convert the value of the pixels to flow 32. The reason I'll tell you, because we'll be normalizing our images. So when we normalize it, definitely the pixel value comes down to be a decimal number. So if it's an integer, it gets typecasted to integer value, and there'll be a considerable loss of data there. Now we stack up this. Temp is that empty list where we store in all these images. Images as in the exact image is not stored. It's an array of the pixel values being stored. Now we stack up all these images. The reason we stack it up is any function on stack is much faster than any other data structure. So we first normalize it. The reason we normalize it is any pixel values between 0 to 255. So basically, we divide it by 255 to bring it between 0 to 1. So now the pixel value is going to be ranging from 0 to 1. This way, the computer detects the patterns faster, and even the training is much faster. Once we have scaled down all the neurons, we again reshape it back into we reshape our stack back to the first element being the total number of elements in our data set, that is the total number of images of cats and dogs. So that is nothing but the length of the data frame. And then 120, remember we resized to 128, 120 in the beginning. We bring it back to those. Again, the values of pixels, we're keeping it as flow 32. We don't need to actually do that in this step because we have already converted to flow 32. Now, the Y labels, the labels were dog, cat. We one not encode it. So basically, most of you would have obviously known what exactly one not encoding is. If an image falls into the class category of dog, it will be 1 comma 0. Since there are two classes now, if the image is of a dog, the value would be 1 comma 0. If it's of a cat, it will be 0 comma 1. So whichever class is representing, that class will have the value 1. We convert back the stacks and the label to array, because that's the most convenient way to pass any value to a model. As I told before, we need to split the data set based on for training and testing. Here we're taking 80% of the data for training and rest 20 for testing. Coming to the major part of Keras, why exactly Keras is like amazing. Because of this, not exactly only because of this, but this is an amazing function, image data generator. Usually when you start working on any of your project, collecting data is a big task, and you wouldn't be able to collect many number of data because collecting data also is kind of expensive. So suppose you say for a specific task, you'll need 5,000 images, but then you have only 2,500 or maybe 3,000. So what you do is you need to augment data. Augmentation of data is nothing but you flip the same image, you flip it, you rotate it with a particular angle, you zoom it into a particular position, and then you do any sorts of operation so that it produces a new image itself. So basically, when you augment data from one single original image, you could produce maybe 5 different copies, which is exactly same, representing the same thing but in a different way. So this even enhances the learning of the model. It reduces overfitting considerably, and more importantly, it gives you more data set. Here is where we specify the values of what exactly to be done. So we rotate the image by 30 degrees, then shift range is 0.1. This if this object, org is the instance of this object. So all these are stored in this instance. Now, since we want to apply to a training data set, we call the instance of that object dot fit, and then we pass in the training data set so that all the operations are applied to it. Oof, that's pretty interesting, right? Let's run this data set. This will take some while. That's why I've given this printing images so that it looks pretty neat. You could see when the cell is done running, there will be a number displayed here, then there will be an asterisk or indicating the cell is running. Okay, let's not just waste our time. Let's go to the next cell. And here is where we're going to define a function that defines our model's architecture. Basically, the input size the model is going to take, the number of layers the model has, and then the output we're expecting, the dimensions of the output we're expecting from our model. Define a function with width, height, and depth, accepting from the user, or rather, when we are calling the function, we would be importing it. Then model equal to sequential. We equate the input shape with a tuple of height, width, comma depth. The depth is nothing but the number of classes, which is 1 in this case. The number of channels, sorry, not classes. So yeah, remember I told you about why exactly we need Keras backend escape. So most of the data sets have a different convention of naming it. For example, the one which we are going to use for our model should have the convention of height, width, the depth, height, and comma the width. Basically, the depth, the number of channels should come at first. That is what our model is expecting. So if k.image data format, we're checking condition if the channels come first, as in the channel value for us in our data set is 1 because we have grayscale. We converted all to a grayscale. If the channels are coming first, we change in the values. For example, initially it is height, width, and depth, having the channel values at the last. Now, if our image data format has channels coming first, we change the input shape. This is only if our image data format is that way. Else not, we'll go on to executing our model. The first layer of a model is going to be a convolutional model with 20 layers, with the height with a 5x5 filter and padding same. What exactly padding same does is, remember I told you when we are after applying convolutional layer, the size of the input image reduces. So padding same makes sure the size of the input image does not reduce and it's the same size of the input image. There's another option you could give it as valid, which lets the input size of the input image to be reduced. And then only the first layer we need to specify the input shape. Here our input shape is 128,1. Then the activation, I'm using relo because that seriously gives a very good accuracy. And then we max pull it with pool size of 2, like I explained in the slides. But in the slide, we are giving strides equal to 1. Here we give 2 strides. Usually, no one can explicitly tell what exactly values you need for this. It comes up with years of practice and maybe even like someone with maybe like 10 years experience also cannot accurately tell what value should these hyperparameters have. So it always comes with trial and error. You give in some values, you check with which values give the best input, best accuracy, and you go on the same. Now these 3 lines of code together constitute one layer of a convolutional neural network. Next layer is the same, but I'm passing 50 filters this time. So I'll be recognizing more features and edges, same activation relo, and then I pass in max pooling. Now, as I told, once when we pass convolutional layer, once we perform this CONTD function, there'll be stacked up of input layers. There'll be like n number of there'll be n number of arrays, I would say, not an input image. So we need to flatten it because when we pass it to a dense neural network, that input isn't accepted. So we flatten it without any loss of data, and then we pass it to a dense neural networks with 500 number of neurons, and then the activation being relo. Then the final output layer would obviously need the number of classes. Right now, it's the number of classes 2, whether it's a dog or whether it's a cat. So the classes value is equal to 2. We have passed it here. And then the activation I use here is sigmoid. Let's define the architecture of the model here. Oof, that's pretty fast. It's done. Now we'll need to call the model the function we defined build. So how do we call it? The class name dot build will give us access to the function we defined. We pass in width value, height value, and depth value, and even the classes. Now the optimizer I'll be using is Adam optimizer, which is gradient descent with a lot of modifications for better accuracy. And then loss is binary cross entropy. Again, like the previous case where Joe explained, there are two possible outputs. Here also there are only 2 possible outputs, whether it's a cat or a dog. The optimizer is Adam. And then the reason I mentioned metrics is to evaluate my model. It keeps displaying what's my loss. There's one catch here. The difference is usually when you train any neural network or CNN RNN, you just directly have model fit train x, train y. But the difference here is since we have used image data generator, we need to call that object and give dot flow, and then pass in the x, the training data set, and then the labels against which you're training. Batch size divides the number you specify in the batch size specifies the number that should be passed at a time. Like now 32 images will be passed at a single time. Then the validation data set is the 20% we split initially will be passed here. And I'm keeping 5 epochs here so that it wouldn't take much time. Also, when you say model.save, model inGenius, that's my model's name here. In Kaggle, your model, once the epochs are done, it'll be available here. Since mine's still training, you wouldn't see it, but I already tried it today morning and I saved a model already. It'll be available here, and then you can save your version and then download it. Before that, it's not available to download. This would take 5 minutes, so that's not feasible right now. Let's go. Since I already have the model downloaded, let's go to it. Let's go to the testing part. I'll show you which image I'll be testing the model with. This is the image of the dog. We need to copy the path of the dog's image, copy as path. Now, I'm not testing it in Kaggle itself. I'm testing it in my local Jupyter notebook. It's open right here. We'll again need to first import our necessary packages. First, keras.load underscore model, because this is what's going to load the weights that we saved from the model inGenius. Then, okay, this is not actually needed, but I know I imported, never mind. Then import cvt2, which is going to read our the dog image. Okay, this is done running. We read our image here. We need to copy paste our path. And then, okay, usually you need to change all the backwards slashes to forward slashes, or it ends up in some Unicode error, which even I don't know what it really means. And then pass in 0 so that it's converted to grayscale. Resize our shape, or do the exact same pre-processing we did before training, as in so that the model doesn't have any ambiguity. It'd be expecting an image with 128,128. And then this is the path of the model that we downloaded. So the way to load a model is tf.keras.models load underscore model. Actually, I should just use load underscore model because I've imported already, but yeah, I didn't think about it. Now let's just run it. It's a dog image, so okay, there's an error. It says there's no such model called inGenius. Fine, let me just copy its path first. Okay, it's not in the downloads. Yeah, it's here. Copy as path. Then paste in load underscore model. The path of the model should be specified. Basically, when you save a model, it's nothing but the values of the weights you're saving, because that's what exactly is learned in any neural network. So now let's just run it. Hopefully this should give us the predictions. Oh god. Good. It has predicted the output as 1, which is referring to a dog. If it was a cat, it would have printed 0 as the output. So this is the basic code for dogs versus cats classification. That's pretty much it. Now Joe would give you a brief insight about what RNNs are. You can take over, Joe.
Yeah, thanks for that, Joy. Yeah, hopefully you can see my screen now. And yeah, so we look at a third application, which is using a recurrent neural network. And the application that we'll be seeing is how do we generate text using RNN. So this is pretty interesting. At least it sounded very interesting to me when I saw this for the first time. And okay, so let's get into that. So let's see how do you think neural net should basically start generating text? Obviously, we are going to feed it some text, some kind of data which is having a lot of text into it, and we will want the neural net to return back a set of text which it kind of learnt it from that huge data set. So let's see, how do we generate text? So now if I say you, I am gonna eat dash. So that can be any food. And if you probably have my data as to what I eat and what I like and stuff, maybe these are the outputs. So 75%, my model might say you're gonna eat a pizza now, or 20% it might say I'm gonna eat a burger now, or 5% might say I'm gonna eat a pasta now. But if I add another sentence before this sentence saying I'm gonna go to McD and then I'm gonna eat dash. So now my model will have to learn the previous statement, and using that context, it should be able to say that 65% you are mostly gonna eat a burger there, or maybe a pasta or a pizza. So you see how this drastically changed the probability because of one extra sentence before that. So this is where context comes into play, and these kind of data. So if we consider generating text, or if we consider generating music, so these are all sequential data. So one data point that appears further in the line will eventually depend on the previous data point that appears ahead. So for all these sequential type of data, we will mostly use recurrent neural network, also called as RNN. Why RNN? Because these are networks which loops. So basically, you remember some amount of information that would have happened earlier, and the neural net will use that memory as well as your input that you are feeding into the neural net. So that's one usage of RNN. And so, yeah, as you see, the input vector contents are influenced by not only the immediate preceding word, but also the entire history of inputs that you have fed it in the past. So let's just quickly look at the different kind of RNN architectures that are present. So the first one you see one-to-one. So this is what we have been using till now. Like in the previous two examples, you saw one-to-one, as in one layer was connected to another. So the red is usually the red that you can see here is the input layer, and the output is the blue layer, and the green vector and green are basically the other vectors. So this kind of neural net is used in image classification, and as you saw in the previous example, and those kind of applications. The next one that you see is a sequence output, one to many. So here you can see that there is one input, and the next layer uses this as an input for the other layer, and eventually it's predicting something. So this kind of neural nets is usually used in image captioning, because I'm only feeding one image and I want a sequence of words to be outputted by the neural net. So this is an application for one-to-many RNN architecture. If you look at many-to-one architecture, um, sentimental analysis, you can take that as an example. So where I feed in a huge amount of, not a huge amount, sorry, a sentence, and then basically the final output should be just a word. So it should say whether I'm having a positive sentiment or a negative sentiment and stuff. So that is where we use a many-to-one architecture, RNN architecture. And many to many, as you see, there are a lot of input, and these input, as you see in the last one, you can ask me what's the difference between the fourth and the last one. So the fourth one, you basically feed in the input first, and maybe you can assume machine translation as an example, where you first feed in all the inputs, and then it translates and then gives you a set of outputs. So that's where that comes into picture. And for the last one, yeah, it's similar to that, but just you're outputting images, sorry, output as and when you feed data. So next, let's get into the code where we generate RNN. And so yeah, this code is also present in my repo. You can have a look at it. It's called rnntext.ipynb. And I would like to give credits to this guy called Canrad, who has a YouTube channel, and even he has his repo. So that was where I saw this code first. And so today, what we'll be seeing is we'll be generating text and using RNN. and we'll be using German philosophers' data. So that data is available in AWS, and they have some set of text data set. And that German philosopher's name is Nietzsche, if I am pronouncing it in the right way. Otherwise, pardon me. So this guy, if you want to have a look at the data set, let me control click and yeah, so this is how the text looks. So this is what I'm going to feed into the model. And yeah, there's some huge amounts of data. So this should be sufficient for our model to kind of learn this and basically give a fake, basically generate a fake text which is written in that style of the author. So that is what we are going to do. So as usual, we import Keras, NumPy. I'll just run maybe as usual. Yeah, so this import is done, and then we provide the path to the file, and since this file is already available online, I just give the URL and then I get the file using Keras. Has a utility function to get the file automatically, and then I open with IO, and I will feed this all of this, and I will feed it as a lowercase. Now why am I doing this? I want my model, I don't want my model to learn what kind of grammar should come. I don't want my model to learn whether I should give capital letter at during the first word of a sentence and all that. I just want my model to kind of learn what word will this philosopher probably say when he's talking or something like that. So that's why I'm converting everything to a model and then I will feed it to a network. So when I run it, you see that it downloads the data from this, and there is about 6,893 characters in this text. So just to say, all right. So next thing that we'll be looking at is how the data should be fed into the model. So obviously I can't provide it as a text directly into the model. I will have to convert it in some sort that the model is able to know what comes next. So if I say A, the model should be able to know that B is the next character or C is the after later character. I can tell that, but my model, it won't know that. So I'm going to create a sequence of tuples which will have character indices. So basically A represented with 1, B represented with 2, and some set of symbols. So that's why you see that the total number of characters is 57. So let me just do that. Yeah. And for this kind of application, you can't run it on a very small data set because data set is going to be very important. Two things that you have to keep in mind is you don't want your output to just throw some garbage characters because it can't learn the style if you give it a smaller data set. And because we wanted to generate original text, this also not only depends on the data set, it will also depend on the tuning of the different hyperparameters of this model and how many epochs we run it for and all this stuff. So yeah, let's go to the next part. So here we are going to create multi-dimensional arrays out of this text data that we inputted. So as of now, the data is in this format in a entire list. So now we'll have to put them in multi-dimension arrays so that I can feed them into the model. So for that, since most I'm using the number 40 here because since I'm assuming this, since most of the sentences don't go more than 40 letters, so I'm using that to make sentences, and the next characters of that this particular sentence. So this sentence, if it starts from ith index to I plus 40th index, the next set of characters will be stored in another array as and when it keeps traveling. So, and then I define my x and my y, and x and y will basically store the boolean. So basically, when I'm running through one sentence, and for the set of characters that appear, the boolean should be one. So that's just to tell that. And then hope I ran the previous cell. Yeah, I'll just run this also. So we have seen different kind of layers. We saw sequential layer, and we are going to use that here too, sequential model. And then the layer that we are going to add here is an LSTM layer. So let me go back to my presentation and show you this slide. So now you see that for the previous two, for the previous two, because of this one sentence, my model should actually change its context and it should predict different values. But now, what if I give a sentence 5 sentences back? So I say I was born in Berlin, Germany, and then I start talking some text. And then after 5, 6 sentences, I'm going to ask you, I speak dash. Now the model should tell me I speak German. Why? Because 4 sentences, 5 sentences back, I told I was born in Berlin, Germany. So how does a neural net do this? We use layers called like LSTMs. So LSTM is called short-term memory. So this is a kind of neural net which has the capability to learn long-term dependencies. So assume it like a memory, and it kind of stores the previous data so that you can do it. So this picture that you see here is like the Keras implementation of LSTM that we'll be using in this text. So here we add the LSTM layer. We say the input size is 40 because I've assumed that every sentence is should have 40. And uh, and the next layer that I'm giving is a dense layer, and I'll be using activation for that, activation as softmax for that. And optimizer wise, I'm using RMS crop here because it kind of gives me better result. You can obviously go check out the Keras documentation to know what are the different optimizers and stuff. So since I don't have much time, I'll just run this through. And um, and just making another sample. I'm just making a function which will kind of generate a sample data set for me. And this is where we feed it into the model and we run it. One fitting, that is one epoch, will take me around 5 minutes, so I can run it. But since from morning I've been running it, so I can just show you the loss, and then it's pretty good. I mean, it's 1.8% loss, so you would expect your model to have predicted something at least. So let me show you the text what it generated after running the model. So I ran some 2 3 stuff. So here you see that it almost kind of generated a pretty good, I mean, it was able to say judgment and impending day and that in Europe and these kind of stuff. So this was like trained only for like 2 3 epochs. So yeah, so this is the application of how an RNN can generate text. And also, one more thing that I wanted to mention about is this callback here. So what this does is sometimes your model might overfit. That means it basically started learning too much that it can go up to basically shoots above what you don't want it to happen. So in this case, you see here, my loss was 1.77, and then the loss just started increasing. And I don't want that because this is like the best weights that I had, and that's why it gave me a lesser loss. So so I asked the model to monitor loss, and then I also say patience is 2. So I wait for another 2 epochs, and once this epoch gave me also a bad result, that is not very bad, but yeah, a little higher result. So you see here that the epoch stopped at 5 out of 6, whereas it should have gone for a 6 out of 6. So that is the different things that you can do with Keras. And further stuff that you can look up after this webinar is you can go have a look up at the Keras documentation. So let me just open that Keras documentation. So here you see, you get started, you see all these different developer guides and how do you write your functional API, how do you write your sequential model and all the stuff. You have plenty of code samples which you can see based on your application. You can see computer vision application, you can see natural language processing, NLP applications, you can see time series application, audio data, and even more generative deep learning models such as GANs, what I referred to. You can run some small GANs and see that. Yeah, so these are the different stuff that you can look up after this webinar. And you can also explore other libraries like TensorFlow and PyTorch. Personally, I prefer PyTorch because I kind of feel it's easy to use and most of the code is available online, so you can see how internally stuff works. And you can also look up at Fast AI, which is like a really good course. And Fast AI is basically a wrapper around PyTorch, so you can easily use PyTorch through Fast AI. And there are very handy methods in FastAI too, like you can search like what is the best learning rate to fit my model and all those stuff. So yeah, and in the next webinar, we'll be exploring how to export and deploy these models. So these models are in your Colab, in your Jupyter notebook and stuff. So we know how to save these models, but where else can I use these models? So when, if you're maybe creating, if you're planning on deploying this model, you can, if you know how to make a Flask app or something, you can just use this model in that Flask app and it'll be able to show you predictions and stuff. There are also two things that you can see. One is Keras JS and one more is TensorFlow JS. So Keras JS is also like a client side of your model. So you can basically deploy your model there and you can see it running. And if you're a web app developer, you want some already pre-trained model to appear on your website, you can use TensorFlow JS. So you can check that out after the webinar. And this is basically the idea phase for the hack. So you have like 1 month left for the hack. So all the things that you can consider right now when you're thinking about projects and stuff is consider the overall skill set of your group. See if you have good web developers, then choose an idea which is related to that. And this is important because in the webinars, in the hackathons that I have attended before, idea is like 50% job done. So even most of us, even during the hack day, we sit and think of what else can I do and stuff. So plan out these 1 month very carefully so that you can kind of think of the different ideas that you can go ahead for the hackathon. Identify really good toolkits which make you which help you out on the last day. So you shouldn't be figuring out what to use on the last day. So figure out good toolkits. And if you're considering deep learning, then obviously Keras is like your best friend, so you can take that. And if you're looking on deploying deep learning neural networks, I would say go for pre-trained model, because in a midnight or in even if 2 days, I don't think you'll be able to train a really good model, and you won't be able to outperform those really good models which are available in the net and stuff in a like a space of 10 hours. So I would suggest you go for deploying. Use your data obviously, but use a pre-trained network and then feed data into that and kind of show your results. So that's it from us. Hope you had a really good session. And Joy, would you like to say anything?
No, that's pretty much from my side. Thanks, guys, for watching it. Take part of the
Yeah,
hackathon. Build some products that's like helpful for someone else. So
sure.
that's
So
pretty
also
much.
we have some resources which are present in the YouTube description. You can have a look at them. We have mentioned stuff where you can learn about more about CNNs, RNNs, and different neural nets, and even find data sets for your ingenious project. And don't forget, the quiz is sharp at 6:45. The time is almost 6:30, so I think we'll let you go now. And also, this is like the last two chances. So today is a chance where you can earn some money into your Paytm wallets. And we also have a last webinar which is coming on the Tuesday, next Tuesday on the 29th. And if you're going to ask me what kind of questions are going to come today, it's very simple. You should be able to answer if you had attended the webinar completely. And since it's a contest, the one or two questions might involve you thinking a little bit and stuff. So that's it from us. We hope to meet you soon in another webinar. And till then, stay safe, stay healthy, and those of you planning to write your internals next month, all the very best for that. Thank you, guys.
Thank you, guys.